Module 9, Section 7.2, Sets. Objectives: identify and use set properties and set notation. Be able to perform set operations. Be able to solve applications involving sets. A set is any collection of objects specified in such a way that we can determine whether a given object is or is not in the collection. We use this notation for set membership. If E is an element of the set A, we will write it this way: E is a member of A. If E is not a member of A, we can use the notation again: E not a member of A. Example: if A is a set of all lowercase letters in the English alphabet, we can write A as the set consisting of all the lowercase letters. Usually we use the uppercase letters to name sets. We list the elements of the set within braces. The three dots indicate that the pattern continues. This is called the roster method of specifying the set. A is a set because we can determine whether an object is or is not in the collection. For example, if 3 is selected, we can say that 3 is not a member of A. A set without any elements is called the empty or the null set. For example, the set of all people over 20 feet tall is an empty set. We denote the empty set using these notations: curly brackets without any listing of members in that, or the Greek letter phi. Set builder notation. Sometimes it is convenient to represent sets using set builder notation. For example, instead of representing the set A by the roster method, we can use A equal to set of all AX such that X is a lowercase letter of the English alphabet. Here we are specifying a rule which describes what the member should be. We get the same set. Another example will be set of all AX has set X square equal to 9. This is the set builder notation. If we list the members, we will get X equal to 3 and X equal to negative 3. These are the two numbers that satisfy X square equal to 9. If each element of a set A is also an element of the set B, we say that A is a subset of B. And we use this notation: A is a subset of B. For example, the set of all women students in a class is a subset of the whole class. If set A and B have exactly the same elements, then the two sets are said to be equal. Remember that the order in which the elements are listed in a set does not matter. We have the following notations: A is a subset of B. A and B are equal. That means both A and B have the same elements. A is not a subset of B. So that means A contains some element which is not listed in B. A is not equal to B. So that means A and B do not have exactly the same elements. Let's do some more examples. Indicate whether the following is true or false. The set 4, 5 is a subset of the set consisting of 4, 5, 6 and so on. If I call this set to be A and this set to be B, we need to check whether members of A are also listed in B. 4 is listed in B. The member 5 is also listed in B. So that means that every member of A is listed in B. So A is a subset of B. So this is true. Second example, indicate whether the following is true or false. 6 is a member of the set consisting of 3, 4, 8. So this is the membership relation. 6 is not listed in this set, so this will be false. Example 3. Indicate whether the following is true or false. The set A, B, C, D equal to the set B, C, A, D. Notice that the members are the same except that they are listed in different order. So that is allowed in a set. These two sets are equal. So this will be true. Set operations. The union of two sets A and B is a set of all elements formed by combining all the elements of the set A and all the elements of the set B into one set. it is written as A union B. So A union B, using the set builder notation, is the set of all X such that X belongs to A or X belongs to B. So in the Venn diagram, the union of A and B is the entire region shaded. Intersection of sets. The intersection of two sets A and B is the set of all elements that are common to both A and B. It is written as A intersection B. So A intersection B is the set consisting of all X such that X will be in A and X will be in B. So it has to be in both the sets. So the shading will be the common region. Disjoint sets. If two sets have no elements in common, they are said to be disjoint. Two sets A and B are disjoint if their intersection is the empty set. For example, the set of rational numbers and the set of irrational numbers are disjoint sets, because we know that a number can be either a rational number or an irrational number, but not both. The universal set. The set of all elements under consideration is called the universal set U. For example, when discussing numbers, the universal set may consist of the set of real numbers, provided we are not speaking about complex numbers here. All other types of numbers like integers, rational numbers, irrational numbers are all subsets of the universal set of real numbers. The complement of a set. The complement of a set A is defined as the set of elements that are contained in the universal set but not contained in set A. That means it is outside the set A. This is the notation for the complement. We write it as A prime, which is equal to set of all X in the universal set, but it is outside A. X does not belong to A. In the Venn diagram, we shade the region outside the set A. So the shaded region is A complement. Let's do an example. We are given three sets and the universal set U. We need to find the union of A and B. So if we write the union, list 3, 6 and 9 that belongs to A, then I need to list members which are coming in B. I don't need to repeat the same element, so I can scan through B and find the next element which is not listed yet. 4 not listed, 5 not listed, 6 is already here, 7 is not listed, and that's it. Intersection of A and B. Intersection means the set of all elements that belongs to both A and B. So if I look at A and B, 3 is listed in both A and B, 6 is also listed in both A and B. The element 9 is not showing up in B, so it will not be in the intersection, and that's it. So this will be set 3, 6. The intersection of A and C. So is the set consists of members of A that are also in C. So A contains 3, 6, 9. C contains 4, 5, 7. So none of the elements are common, so this will be the empty set. So A and C are disjoint sets because the intersection is empty. We can also write this notation here. Complement of B. Complement of B is all members in the universal set which are not listed in B. So I can look at B and the universal set U. So 1 is in the universal set but not in B. 2 is in the universal set but not in B. 3 is in B. I cannot list it in the complement. 4, 5, 6, 7. They are also in B. So that will not be in the complement. We have 8 in the universal set and 9 in the universal set. So B complement is the set consisting of 1, 2, 8, 9. So this is another example. We need to draw a two-circle Venn diagram and shade the region corresponding to A complement union B. So A complement means everything outside A, and union means we need to also include members belonging to B. So if I shade A complement, it will be outside A within U. So this is the shading for A complement. Union means I can also include members of B. So part of B is already shaded, but there is another part of B that needs to be in the union. So I need to also shade this portion. So that will be the shading of A complement union B. So in this example, we need to look at this Venn diagram and find the number of elements in the union of A and B. So if we use the notation small n of A union B equal to the number of elements in A union B, I can look at the region. So A union B will be these three regions here. There are 40 members in the first region, so that will be 40 plus we have an extra 6 more in the common, so that will be 6, 21 in the rest of B. So when we add these two together, we are going to get 67. One more example. How many elements are in the set A complement? This is the A complement notation. So A complement means outside A. So we cannot count these two regions, which is in A. So anything outside A is fine. So we have a 22 here that is counted. Then we need to look at outside A and B, but there are no members listed here because we are not seeing a number in that region. So this is all the counting for A complement. So we can say that this is equal to number of elements of A complement, the notation small n of A prime. An application problem. A marketing survey of 1,000 commuters found that 600 listened to the news, 500 listened to music, and 300 listened to both. Let n equal to set of commuters in the sample who listen to news and m equal to set of commuters in the sample who listen to music. Find the number of commuters in the set n intersection m complement. Using the notation small n of A is the number of members in A, we are asking for small n of n intersection m complement. Here is the solution. We use the Venn diagram. The set n consists of the green part and a red part. N has 600 elements and the red part has 300 members, so the green part must be 600 minus 300 equal to 300. So we can put the numbers in this Venn diagram and we will get this. So 300 listen to both music and news, then 300 listen to news but not music, and 200 listen to music but not news. And because we have 1,000 total in the survey, if you add these three numbers, we will get 800. So that leaves 200 outside these two circles. So 200 people listen to neither news nor music. And our set is n intersection m complement, which means that it should be in n but not in em. So if you look at this Venn diagram, the region is the green region here. Is part of en, but it is outside em. Outside em means they are not listening to music. So that count is going to be 300.